Hello, curious minds. Quick question. When sunlight falls on a shiny steel plate, nothing special happens. But if the same sunlight is reflected by a concave mirror, boom, you can burn a piece of paper. Now, why is that? It's because the concave mirror brings all those parallel rays of light together to meet at one single point on the axis. That point is called the focus, denoted by F. And here's the twist. Since the rays actually meet, this is called a real focus. The concave mirror is like a good party host. It gathers all the guests' rays and makes them meet in the middle. Now let's see what happens with a convex mirror. Shine parallel rays on it, and instead of coming together, the rays scatter out. They run away like kids after the last school bell. But when you extend those scattered rays backward, they appear to come from a single point on the axis behind the mirror. That point is called the focus F of the convex mirror. And because the rays don't actually meet there, it's called a virtual focus. So convex mirrors are like that friend who says, "Meet me at the cafe," but never really shows up. It only appears they're coming from there. Now, let's measure things properly. The focal length of a mirror is simply the distance from the pole P to the focus F. We represent it with the letter F. So the relation is F equals PF. In symbols, F equals PF, that's it. Just a straight line distance along the principal axis. This length is super important because it shows up everywhere in mirror formulas and ray diagrams. Think of it as the mirror's unique ID number. No two mirrors of different curvatures have the same F. Now here's a slightly advanced idea, the focal plane. Not all rays are perfectly parallel to the axis. Some come in at a tilt, inclined to it. When a tilted parallel beam hits the mirror, it doesn't meet at the axis. Instead, all those rays meet at a point in a plane that passes through the focus and is perpendicular to the axis. That entire plane is called the focal plane. So imagine the focus as the star of the show and the focal plane as the stage on which many of axis rays get their spotlight. Hey there, physics explorers. Let's compare two personalities in the mirror world, the concave and the convex mirror. Look at the diagram on the left first. See those parallel rays? After reflection, they actually meet at a single point on the principal axis. That's the focus F of a concave mirror, real, because the rays physically gather there. You could literally put a paper at that point and watch it burn under sunlight. Concave mirrors are like collectors. They gather light like a friend collecting gossip. Now glance at the right diagram. The convex mirror plays the opposite trick. Parallel rays hit the mirror and scatter outwards, diverging. If you extend these rays backward with dotted lines, they seem to meet at F behind the mirror. But remember, it's only an illusion. The rays never meet in reality, so we call this a virtual focus. Convex mirrors don't collect light, they spread it, like someone spreading rumors in the entire class. So, here's the big difference. Concave is equal to real focus, gathers light. Convex is equal to virtual focus, scatters light. And that's why a concave mirror can set things on fire, while a convex mirror can only make you look smaller, no burning, just shrinking. Let's solve a quick one. Suppose a concave mirror has its focus located 12 centimeters away from the pole. What is its focal length? Step 1. Recall the definition. Focal length F equals PF. Step 2. Substitute the value. PF equals 12 centimeters. Step 3. So F equals 12 centimeters. That's it. Always remember, the focal length is just the distance from the pole to the focus, nothing fancy. The trick is identifying whether the focus is real, concave, or virtual, convex. So let's wrap this up beautifully. Concave mirrors converge parallel rays at a real focus. Convex mirrors diverge rays, but their backward extensions meet at a virtual focus. The focal length, F equals PF, is the key distance for all mirror equations. The focal plane explains what happens to tilted parallel rays. In short, concave mirrors bring light together, convex mirrors spread it apart, but both obey the same simple rule of focus and focal length. So next time you're in sunlight with a shiny mirror, think twice before playing around, because physics doesn't just reflect, it also burns. That's it for today. Keep reflecting, keep focusing, and I'll see you in the next session with more light bending fun.